Let's suppose we have this passenger car with a 2.5 meter wheelbase with 52% of the weight on the front wheels when it's sitting on level ground. We want to know, what's the center of mass of this car located? Where is the center of mass? Let's try drawing a free body diagram and applying our equations of static equilibrium to find this. Here's our free body diagram. We will draw the car after establishing some axes and label some relevant points. We'll then apply all the external forces, starting with the weight. This is acting at the center of mass, which we don't know where that is, but we know that it's going to be offset from one of these wheels by some unknown distance x. So we'll place it there, and then we can solve for that x to tell us where is that center of mass. We'll then include the forces acting on the wheels. And you can see if 52% of the weight is resting on the front wheels, that means that the reaction force from the ground acting back on the car due to Newton's third law has to be that same 0.52 of the weight, or 52% of the weight. Similarly, on the rear wheel, that 0.48 becomes 0.48 acting up on the wheel from the ground. We have all the forces put in now, and now we need to find that unknown distance x. We can use our equations of static equilibrium, which are sums of the forces in any direction or sums of the torques about any point. Let's start with sums of the forces in the x. Just for kicks, there are no x forces. So this says 0 is equal to 0, which is true, but not very useful. Next, let's consider the y forces. We have acting upward our 0.52 weight and 0.48 weight, and then we have acting downward the weight. So 0.52 weight plus 0.48 weight minus the weight is equal to 0, which gives us 0 is equal to 0. Again, a true statement, good, but not terribly useful. And like Goldilocks, we move on to the third, sums of the torques. We can choose any point to sum our torques about. I'm going to propose we choose the rear wheel because that's where I have my x coming from. And in practice, what we then do is we do RF sine theta for each force being applied here. And if we think about what that would mean is we would have to then try and find this position, but we don't know the y position either. Luckily, it doesn't matter because that RF sine theta is just giving us the perpendicular component. And we already have the perpendicular distance is x. Because our force is acting straight down, x is the perpendicular distance. So we don't need to get the actual lever arm. We can just use x times w for what that torque is. We'll call counterclockwise positive, and this weight w is trying to go counterclockwise about my pivot point r, which means that it will be a positive contribution of x times the weight w. And this 0.52 weight will be a negative contribution because it's trying to go clockwise times its lever arm of 2.5 meters. So we get xw minus 2.5 times 0.52w equals 0. We can divide out by the weight, which is good because we didn't actually know it. And it cancels, leaving us with x minus 2.5 times 0.52. We can add this term to both sides and get our position of 2.5 times 0.52, or 1.3 meters. This tells us that the position of the center of mass of this car is 1.3 meters away from the rear wheel.